Hello, everyone. Welcome to today's live broadcast, Improving the Separation and MS Detection of Proteins and Protein Fragments by using new mobile phase options in reversed phase HPLC and UHPLC. I'm Laura Bush, the Editorial Director of LCGC, and I'll be your moderator for today's event. We're delighted to bring you this educational web seminar presented by LCGC and sponsored by MacMod. A company should be able to condense its mission statement into a simple phrase. MacMod's mission statement is smarter chromatography. But you may ask, just what does smarter chromatography mean? It means that when they make a recommendation to you about an HPLC or UHPLC product, it's to partner with you to offer innovative solutions to your complex problems. They use advanced, state-of-the-art analytical software to match their product portfolio with your separation needs. They leverage their company's 29 years of experience in the LC column business, their technical expertise, and manufacturing network to help you solve your toughest application problems. MacMod provides up-to-date and accurate technical catalogs and reports from industry-leading separation scientists to keep you informed of new technologies. That is what smarter chromatography means. We have a few housekeeping announcements before we get started today. The webcast is designed to be interactive, so we encourage you to ask questions. You can submit questions at any time by typing them in the Q&A box, which you can find on the right-hand side of your screen. You can enlarge the slide window by clicking on the small green icon in the upper right-hand corner of your slide window, or by hovering your mouse over the lower right-hand corner and dragging the window to the desired size. The slides will advance automatically during the webcast. If you have any technical problems viewing or hearing the presentation, please click on the question mark Help widget in the dock at the bottom of your window. Please also note the valuable resources made available on the left-hand side of your screen that are provided by our sponsor. I would now like to introduce today's speaker. We're very pleased to be joined today by Dr. Barry Boyes. Dr. Barry Boyes is the Director of R&D for Biosciences at Advanced Materials Technologies in Wilmington, Delaware. He's also an adjunct professor of chemistry at the University of Georgia and the CSO of Glycoscientific, LLC. Barry started his career in biochemistry at the University of Alberta, completing his PhD in neuroscience at the University of British Columbia under the supervision of Professor Edith McGeer. After work at Central Research at the DuPont Company in Wilmington, Delaware, he joined Drs. Kirkland and DeStefano at Rockland Technologies, where he developed a successful program to commercialize a variety of separations products and technologies for proteins and peptides. HP acquired Rockland in 1997, and Barry stayed with the company, which later became Agilent. At Agilent, Barry served in a variety of roles in R&D and product development, becoming a senior R&D manager for separations, consumables, and services, then the bioreagents business, bringing to market a range of nucleic acid and proteomics analysis products. In 2006, he became the VP of R&D at Smith Detection, commercializing field-ready biothreat detectors for infectious and toxic agents using a variety of biochemical and spectroscopic technologies. In 2009, Barry returned to full-time pursuit of technologies for high-resolution biomolecule analysis, using novel technologies pioneered at AMT for superficially porous particles. Since then, his efforts have focused on peptide, protein, and glycoprotein analysis, using LC and LC-MS analysis. Barry, thank you for joining us today. You have the floor.
Okay, thank you very much, Laura. It's a pleasure to be here today, and I'd like to thank our partners at MacMod Analytical for the opportunity to share some information that I hope will be useful to the audience. And I'd also like to apologize to Laura for that rather long introduction for me. With that said, let's jump into this. What I'd like to share today is some additional or new alternatives for separations of proteins and peptides. The discussion today will really focus more on methods of use than materials, but it's necessary to discuss some of the materials that have been used during the past several decades for HPLC separations. If you're going to, as our purpose is, improve separations of proteins and peptides, there's a comparatively short list of technologies that can be applied to speed things up or to give you greater resolution of your mixtures. These are shown on the slide in front of you. Certainly in the last several years, the first on this list has gained greater attention, that is the use of smaller particle packed bed materials for HPLC columns. Now, such packed beds can be formed in a number of ways. They can be formed from totally porous particles, also referred to as fully porous particles. Those which have no pore structure or not porous or polycular materials, and the partly porous materials. And this is where we'll focus most of today's attention, is on these partly porous or so-called superficially porous particle packed beds. Now, these are not the only options. There are other formats that have at various times been discussed and have a variety of useful roles in separations. These include monolithic materials, as well as a variety of different formats of open tubular columns or channels. These are, of course, the chip-type format that has been increasing in popularity in very recent years. None of these will really be discussed past the superficially porous materials. That's where today's examples, which are very much focused on what we can do in protein science. Now, the agenda for today's discussion will really, to set the agenda, we continue to have an ongoing challenge, technical challenge with separations of proteins and peptides. That's because these are generally not trivial mixtures, and any opportunity we have to either speed things up or improve our resolution of these complex mixtures is generally useful. The complexity is really a reflection of the complexity of the molecules that we're talking about. With protein mixtures or fragments of mixtures, we're dealing with relatively high molecular weight analytes that have a variety of charges. That is to say, they are polyelectrolytes. They can have great inherent heterogeneity due to post-translational modifications or pre- or post-synthetic chemical modifications, and that these chemical alterations can change over time in response to a variety of environmental conditions that the sample can be subjected to. So, predominantly as a consequence of the higher molecular weight of the analytes, we can refer to what I'll mention in today's discussion as diffusional or mass transfer limitations, which reflect the size of the analytes of interest. That is to say, when you get an increase in molecular weight, that is larger molecules, they don't diffuse through free solution as quickly as small molecules. And this is generally reflected in the conditions and materials of use that are required for liquid phase separations. Now, because of the inherent complexity of the analytes that we're interested in, I do not want to give you the impression that there is a singular technique or technical approach to resolve the analytical challenges for protein or peptide analyses. So we're generally talking about a combination of methods and approaches. Today's discussion will largely focus on reverse phase methods, but please have an appreciation that this is not the only thing that I believe to be important. So when we think about where the major improvements have been in protein analytics, certainly the rise and continuing popularity of LC methods coupled with mass spectrometry is amongst the first things that I think of. In terms of mass spectroscopic instrumentation, there's been massive improvements, particularly during the last couple decades. We won't really discuss a great deal of that today, but we can certainly assume that as we look several years out, we'll be talking about even greater capabilities in mass spectrometry. I would argue that there have been a number of developments in mobile phase characteristics, not all of which will be discussed today, but certainly in terms of charge manipulation of electrosprayed analytes, as well as some of the things that I'll talk about today. This is making LC-MS analyses of larger molecules a more tractable challenge. There's also been remarkable improvements in stationary phase materials, and this is now winding its way down into protein analytics. Today's discussion will really focus more on superficially porous particles, particularly for protein analyses, but clearly also for fragments, including peptides, as well as larger polypeptide fragments. So, as I mentioned in today's discussion, we'll be focusing really on the use of superficially porous particles. Now, Advanced Materials Technologies and our company has been actively engaged in pursuing these materials across actually several decades for some of us, but particularly during the last decade, where we brought to market a number of new materials that we feel to have enabled the use of superficially porous particle technology. And this has become a very rapidly growing and popular format for packed column separations in the liquid phase. This is actually a picture of a material which we commercialized about a decade ago, a 2.7 micron superficially porous particle. And the reason why we call it this is, of course, the solid core at the center of the particle, composed of impermeant silica, a fused material, surrounded by a porous shell, which in this case is a half micron thick shell, with the surface area supplied with that porous silica shell material. Of course, for reverse phase, these are all chemically derivatized materials, and we'll talk about that a little bit. But the reason why we feel this is a particularly valuable material for packed column bed chromatography is that it helped to address the then emerging competition with increasingly small particles, that is sub-2 micron porous particles, without the need for everybody to immediately upgrade to very high pressure equipment. The materials that we'll be discussing today are all above 2 micron particle diameter, and because of that, there's no need for frits to keep the materials in the column, which are very small fritted materials, for example, half micron. Well, because of this, that actually simplifies some of the sample handling characteristics. But the driving purpose for a superficially porous particle morphology is to maintain high resolution at higher linear velocities. That is, to reduce analysis time while still allowing high efficiency. So today's examples in peptide and protein separations will all use a variety of formats of superficially porous particles. I'll try to remember to point out the characteristics of the materials as we go through this. But the focus of today's discussion is really mostly around mobile phase characteristics that are required for useful LC-MS applications. On this slide, I make the not terribly bold statement that successful LC-MS requires that you have a stationary phase, that is the column, mobile phase, and instrument that are properly tuned and assembled so that they can work in concert to achieve your task. Now, for protein and peptide separations, that has historically meant that there is a challenge between the use of mobile phase modifiers, particularly acidic modifiers, that are useful chromatographically or beneficial chromatographically versus those that perform better for mass spectrometry. Now, historically, trifluoroacetic acid has been the acid of choice for chromatographic reasoning. And we'll go through some of the examples why that is the case in a moment. But we can compare this with the use of formic acid, which performs very well for LCMS applications. So what I mean to say here is that we have this comparison between two different acids, one of which shows particularly good for performance for the separation goals, and one that shows particularly good performance for the mass spectroscopic goals. Two acids each has thus a compromise in terms of what our ultimate requirements are for an HPLC method. So between formic acid and trifluoroacetic acid, I think that we cover probably 95% of all current applications. There has also been, various examples in the literature of modifying the other components of reverse phase separation, that is the organic modifier. And this is not an unimportant thing, but there has been comparatively little systematic analysis of how one might do that in order to optimize the separation. One of the great improvements from my view is at least the acceptance and common application of elevated temperatures for protein and peptide separations and for LCMS applications. And I would reiterate that in almost all of the examples we're going to look at, the operational conditions include column heating at 60 degrees or above. Now, the first foray we had into this was several years ago, and I'll point out a reference here from 2012 on the bottom of the slide where we discussed this in some detail. But the original purpose was to address this difficulty we had between what was good for mass spectrometry versus what was good for chromatography. On the top example here is separation of, on your left side, the chromatogram at the top is conducted in 0.1% trifluoroacetic acid, separation of a fairly simple 5-peptide mixture. And you can see that the peak shapes are narrow. The peaks are relatively symmetrical, and we get a reasonable separation. In the middle panel, we see 0.1% formic acid as the mobile phase acid modifier, and it's apparent that the peaks are much broader. There is some peak tailing and a less desirable but nonetheless useful condition. In the bottom, all we've done is to take that 0.1% formic acid and modify it with its conjugate base, in this case ammonium formate. So we've increased the ionic strength of the mobile phase conditions, and this has resulted in an increase in both retention as well as improvement of peak shape, that is peak width, as well as tailing. So a simple fix for this problem, and I would argue if you view the table, the most obvious correlate for this would be with ionic strength of the mobile phase. Now, this reasoning is also described in a second reference that I included on the slide from David Macaulay, who actually observed this many years before we had taken a look at using these kind of conditions. He had described this, in fact, in 2004, and we can both confirm as well as extend those observations that ionic strength seems to be a driver for relatively poor performance in 0.1% formic acid, and that the reason for this is the rather weak, that formic acid is a rather weak acid and does not fully dissociate and generate sufficient ionic strength. Now we can see this really as in this example we've taken the previous results and plotted both tailing factor for 2 of the 5 peptides as well as peak width as a function of the mass of material loaded onto the column. And what we see again reiterates that this is likely a result of low ionic strength in a mobile phase. The system overloads, that is, it shows so-called nonlinear isotherm behavior. As the mass of the material is increased, we get increasingly misshapen peaks that are broader. So a relatively easy fix for this is to increase ionic strength by adding a neutral salt. And we've done that and detailed it somewhat for LC-MS applications. In the example on the screen in front of you is a capillary separation of a tryptic digest, where we've looked at, in this case, a relatively simple protein, apomyoglobin, and the sample was resolved using LC-MS in either formic acid or formic acid modified with a little bit of that neutral salt, that is ammonium formate. And as you can see, the separations are overall rather similar, and the mass spectral intensities are rather similar, and the mass spectra themselves, shown on the bottom, have a similar site occupancy, ionization occupancy. So relatively modest change in terms of the conditions, but net effect is an improvement in the chromatographic separation part of the LC-MS experiment. Now, protein chemists, like many biochemists, are fairly conservative people, and that might be a nice example, but we needed to go through and produce a more fulsome proof statement on this. So what we did was undertake a proteomic analysis, in this case, looking at either synthetic proteolytic digests, a mixture of proteins that were trypsin digested, and then look at essentially the statistics of the proteomic analysis in terms of IDs that could be obtained, number of peptides that could be identified, and corresponding proteins, as well as sequence coverage. We did this not only for a mixture of a synthetic mixture of standard proteins, but we also did it in a more realistic proteomic analysis looking at canine prostate samples, so soluble canine prostate proteins. And the results from this are shown in the, for those of you who are interested, in the reference attached to this slide, but the net effect was better protein IDs, a greater number of proteins identified in a proteomic sample, and all of this results from essentially improved chromatographic separation with no net detriment to the online mass spectroscopic performance. So with these results in hand, it caused us to rethink if we were overlooking an opportunity to broaden our scope, to look at a larger list of potential acid modifiers and their potential benefits to the chromatographic part of an LC-MS experiment, and in particular, what characteristics do we really need to have in order to carry out effective LC-MS analyses? And that list of potentially useful or required characteristics is shown on this slide. Now, first and foremost is, of course, you must have a volatile component. The last thing we want to do is plug our electrospray interface in the mass spectrometry experiment or to gum up the capillary ion path. The second that we tried to look at was so-called Henry's law coefficients, which describes the, again, ability to volatilize a component from aqueous solution. As it turns out, many Henry's law coefficients are just not available for the things that are most potentially useful. And of those things that we identified as most potentially useful, all of them have low pKa. That is, we want something that is going to be a readily dissociable acidic modifier so that we would have sufficient ionic strength, in other words, not recreate the chromatographic problem, but allow us to conduct electrospray ionization without suppressing the ionization of our analytes of interest. Now there's an additional set of criteria here, which is we're going to use this for protein and peptide analysis, and in order to be useful for protein and peptide analysis, we want those components that will favor solubility. It is frequently overlooked, or in some cases unthought of, that if your sample doesn't remain fully soluble, then useful interactions with the chromatographic surface or proper ionization and electrospray processes will be impaired. So it remains difficult to say exactly what characteristics would best predict these requirements. But we did nevertheless look at a very large number of materials which might exhibit these desirable properties. The slide in front of you shows a table with some of the materials. It's actually a much longer table or collection of modifiers that we have looked at. Those in red are ones that have been reported in the literature previously. Most of them are fluorinated materials, and included in this is a variety of halogenated and fluorinated carboxylic acids and weak acids that we have also studied in some detail. Now, I will point out on the last column, I've identified as biological hazard, and the reason for this is some of these we did not actually look at because once either having received them or become aware of them, even though they might predict useful properties, we found to be sufficiently toxic that we would not use them in the lab. In particular, fluoroacetic acid here, labeled in yellow in front of you, I would ask you not to bring into your laboratory as it is a chemical warfare agent, and therefore just a little bit undesirable when your EHS people come around. So the various acids in this table, as well as many others, we looked at in terms of their potential utility, and in many cases looked at them chromatographically, and in fewer cases than that, looked at them for coupled LC and MS applications. On the slide in front of you are those we have studied in greatest detail. These include, of course, formic acid, acetic, trifluoroacetic, difluoroacetic, and 3-fluoropropionic acid. Again, these examples are not representative of all the things that we've tried. However, these are the ones that we found to at least fulfill the requirements of useful electrospray ionization, a relatively low toxicity, and acceptable performance chromatographically. So the ones that I'm going to focus on the most are really formic acid, trifluoroacetic acid, and difluoroacetic acid. I'll show you many examples of those, as well as comparisons with a mixture of ammonium formate and formic acid. On the slide in front of you is the separations that were obtained from a mixture of 5 peptides. varying from about 500 mass to 3,500 mass. The top set of panels is with the UV detector, that is absorbance at 220 nanometers. The bottom panel shows the total ion current generated for the online LC-MS. A lot of work that we do in the lab uses multiple detectors, that is UV in series with mass spectrometry or fluorescence in series with mass spectrometry. And in this example, in the top panel, you see the UV representation of that separation. And with formic acid, and this is a straight gradient elution chromatogram using acetonitrile with a halopeptide ESC18 column under otherwise pretty typical conditions for peptide separation. With formic acid, an acceptable but not really high performance separation, we can see that relative to the ammonium formate, formic acid, trifluoroacetic acid, or difluoroacetic acid, that there is band broadening, the peaks are broader, there is a little bit of tailing. We can see this whether we're looking in UV or in the mass spectrum. When we look at the mass spectroscopic data, we can see that there is good signal intensity, as there is with ammonium formate, formic acid, and reasonable intensity with difluoroacetic acid. But with trifluoroacetic acid, we are significantly suppressed in the ionization for all of the peptides. Now, in order to summarize some of this for these 5 synthetic peptides, I've shown just the mass spectral data for that separation, as well as the multiple ion chromatograms. That is, the chromatogram, the top panel shows the total ion current. The numerical data shows the integrated multiple ion chromatograms. That is, the selected ions obtained for each charged state of each of those peptides. So this is a more reasonable means to integrate that data because it includes all charged species for each of the individual peptides. Those are then summed and then compared across the 4 different mobile phase conditions. And again, the numbers there numerically, there's a summary of that data in the bar graph on the bottom. And what you see is that trifluoroacetic acid profoundly suppresses the mass spectral signal by a factor of 20 to 50-fold. Difluoroacetic acid mildly suppresses or moderately suppresses the ionization, that is the mass spectral signal intensity, by a factor of about 3 to 4-fold, whereas formic acid remains having the chromatographic challenge of broader peaks and somewhat tailing. We've seen this broadly with peptide mixtures, synthetic peptides, as well as tryptic digest peptides. This slide shows an example with a tryptic digest peptide mixture, in this case using reduced and alkylated enolase, which was then tryptically digested and underwent reverse phase analysis, in this case again on a halo peptide ESC18 column under typical tryptic digest conditions, and in this case showing the mass spectral data. If we look at the total ion current on the top for using difluoroacetic acid as the mobile phase modifier, we can compare that to formic acid in the middle panel, and we see it's not as intense, but certainly much better than what we see on the bottom panel, which is the use of trifluoroacetic acid. So again, just reiterating what we had seen with synthetic peptides with a more complex mixture, in this case, a tryptic digest. Now, we have looked at this actually with 5 different mobile phases, again, comparing acids, and we see the same overall pattern throughout with peptides, which is the significant increase in ionization suppression with trifluoroacetic versus difluoroacetic acid. And when we have looked at now over 400 peptides, we see that difluoroacetic acid is about the same performance overall as we get with a mixture of formic acid and ammonium formate, a little bit less variable, a little bit more suppressed than we get with the ammonium formate formic acid mixture, but that formic acid generically shows an impaired chromatographic performance. Now, this has worked reasonably well for peptides. What about proteins? And this is an example separation of a 5-protein mixture using, again, UV detection in series with mass spectral detection. So UV on the right, mass spectrum, UV on the left, mass spectral data on the right. And restricting ourselves to the UV data, we can see that, as expected, trifluoroacetic acid shows a very good peak shape, high efficiency separation. Formic acid, we actually increased the concentration to about 50 millimolar, a little bit over 50 millimolar, 0.25% formic acid, because 0.1% formic acid generically for protein chromatography looks quite bad. So in the third panel down, we can see difluoroacetic acid exhibits a similar performance in terms of peak shape and resolution to what we get with trifluoroacetic acid, whereas 3-fluoropropionic acid, again at 0.1% in the mobile phases, is similar to what we see with a formic acid mobile phase and inferior to what we get with either trifluoroacetic or difluoroacetic acid. If we look at the mass spectral data, we see the converse to be true. The worst performance is with trifluoroacetic acid, whereas the best is with formic acid and 3-fluoropropionic acid. And by best, what I mean is the most signal intensity, but still rather compromised chromatographic performance. Difluoroacetic acid certainly fares much better in terms of protein separations. There is some ionization suppression, not as much as trifluoroacetic acid. So here is the compromise, which we haven't completely resolved, which is that the best chromatographic performance is also the poorest mass spectral performance. Now, do these conditions do anything strange to the mass spectral data itself? That is, the occupancy of the different charge states. Of course, protein mass spectrometry always exhibits the multiple charge states. We use these multiple charge states to deconvolute and obtain accurate mass data or estimates of the mass of an intact protein. And in this case, what I've done is calculate the average charge state under each of these mobile phase conditions, and you can see that they're not remarkably different. They all exhibit multiple charge states. The charge state envelopes look relatively similar. The average charge states are highest for formic acid and lowest for trifluoroacetic acid. And difluoroacetic acid resides somewhere between the two. Again, useful deconvolution of these spectra can be obtained under any of the mobile phase conditions. Now, if we try to get some quantitative impression of what's going on as we alter the mobile phase conditions, what we see, and I'll speak in generalities now, although the precise data is here, is that if we want to use formic acid for useful protein chromatography, we need to be at relatively high concentrations. In this case, looking at the peak width as a function of concentration for each of these acids. For formic acid, we need to be around 50 millimolar or above in order to get good peak shape. For TFA, 5 millimolar above seems, adequate. Same thing, roughly speaking, for difluoroacetic acid, whereas with 3-fluoropropionic acid, we need to be at 20 millimolar or above before we get to a plateau. If we look at a similar quantitative approach or comparative approach for the mass spectral intensities, with formic acid, we begin to suppress as a function of concentration for the total ion current, and this suppression is continuous, plateauing somewhere in the range of 50 millimolar concentration, with trifluoroacetic acid around 5 millimolar, a little bit higher for difluoroacetic acid, around 10 millimolar, and you can actually go up quite high, comparatively speaking, with 3-fluoropropionic acid before you've completely suppressed the signals. So to summarize those observations, or attempt to summarize it, is shown in the next slide, where we have a bar graph comparing on the left-hand side of your screen the mass spectral peak area for total ion current for, in this case, showing 4 proteins. We've looked at a much larger group. Not all of that. This is representative of a much larger data set. I got a rather loud beep here. Is there a problem on that end?
No,
Hello?
the sound is fine.
Okay, thank you. Comparing the performance for total ion current intensity with 3-fluoropropionic, difluoroacetic, and trifluoroacetic relative to the results obtained with formic acid, which would be 100%. So we picked conditions which were best for formic acid intensity in this experiment. And you can see that we have significant ionization suppression with difluoroacetic acid, but not nearly as much as we get with trifluoroacetic acid. If we look at the right-hand side, where I've cleverly labeled it better towards the bottom, this is peak width, in other words, chromatographic performance. And it is best with trifluoroacetic acid and very nearly equivalent or more similar with difluoroacetic acid. So the conclusion here is that we see some of the same characteristics that we observed for peptide separations. In other words, we have to give away something, which is some ionization intensity, in order to improve the chromatographic part of the equation.
Barry, just a quick time check. We should probably try to go to Q&A in 10 to maximum 15 minutes.
Okay. I'm going to speed it up a bit on this end. So this is another example showing a comparison of formic acid, difluoroacetic acid. In this case, a separation on a capillary LC example for the separation of hemoglobin subunits. And what I'd like to point out on this one is that the difluoroacetic acid, again, shows much improved chromatographic performance relative to formic acid, and sufficiently so that the peak intensities are in fact quite comparable to what one obtains with formic acid. But of course, the peak shapes and ability to resolve minor variance between the alpha and beta hemoglobin subunits is sufficient. So even though we are getting some ionization suppression, the peak intensities are comparable due to the narrowed peak width, and certainly the chromatographic separation is greatly improved. We see this observation in terms of chromatographic performance with larger proteins. Hemoglobin subunits are around 15,000, 16,000. In this case, we're now looking at a monoclonal antibody separation. In this case, with a protein C4 400 angstrom pore size material, looking at formic acid on the top panel, difluoroacetic acid in the middle, and trifluoroacetic acid on the bottom. And what you can observe is that both difluoroacetic acid and trifluoroacetic acid will generate useful chromatographic performance, whereas formic acid will not. I'm going to very briefly touch on some considerations of the interplay between materials, superficially porous materials, and how we design them to take advantage of these improvements of chromatographic modifiers in the mobile phase. So what do we need for a good protein separations? Well, the first thing we need is very wide pores. Pore size must fit the molecule size in order to eliminate or reduce the diffusional limitations that one obtains for such molecules making it into the superficially porous particle structure. We have recently commercialized the 400 angstrom pore size material. This slide shows a cartoon representation of that on the left and the scanning electron micrographs of this material on the right. These materials have an enlarged pore size in order to fit larger protein molecules into the superficially porous structure. This is important because it improves peak shape. In this case, showing an example of a standard protein separation using trifluoroacetic acid in the mobile phase, and a comparison of a superficially porous 400 angstrom material on the top panel to that of a 300 angstrom material on the bottom panel. And you can see the improved peak width on the superficially porous material on the top panel, particularly true as the molecular weight of the proteins are increased. So, for example, catalase and enolase are improved by nearly 50% in terms of their peak widths relative to what we get with a sub-2 micron, 300 angstrom superficially porous material. I'm going to skip this slide and go to the next, where we're looking at, in this case, a monoclonal antibody separation on a wide pore in the middle panels, 400 angstrom material, compared to the sub-2 micron, 300 angstrom pore size material, nearly half the peak width. And when we increase the peak, or the pore size to 1,000 angstrom, which is a material that will be commercialized this fall. This is a prototype material, but we are working rapidly to commercialize it because of the considerably improved peak width and resolution of minor components compared to a typical sub-2 micron, 300 angstrom pore size material. And this is, in this case, showing the resolution of trastuzumab and some of its minor variants in this biotherapeutic molecule. So 150,000 molecular weight, you really begin to see the effects of pore size on peak width and chromatographic performance. In this case, again, we're using difluoroacetic acid as the mobile phase modifier. And our reason for this, I'm going to skip through some of these slides in order to now focus on why the provision of alternate mobile phases is particularly important when you begin to look at, for example, therapeutic monoclonal antibodies. Now, this is typically the way IgGs, intact IgGs, are characterized, where we have a mixture of glycoforms, variants of the therapeutic monoclonal antibody, with glycosylation variants being quite obvious. When we zoom in on the mass spectrum, we can, in fact, see the multiple, at each charge state, we can see the multiple masses associated with each of the glycosylation variants. We can deconvolute this mass spectral data in order to get a measurement of the intact IgG, in this case on the bottom right-hand side. You can see the mass of the IgG with each of its glycosylation variants. We know these to be the glycosylation variants because of the correspondence of the mass differences in each of those intact molecules. What is also apparent is that in addition to those glycosylation variants, there are additional variants that appear in the deconvoluted mass spectral data, and we're not always confident that we know whether those represent additional variants in glycosylation or variants in the IgG polypeptide backbone. That is, at the protein level versus the glycosylation variants. Now, in order to undertake such an analysis, we can, in this case, deglycosylate the intact monoclonal antibody and compare chromatographically and with online mass spectrometry what are the masses and what are the chromatographically resolved variants. And we can see after the main peak, in this case for both the deglycosylated and fully glycosylated, that is intact native structure, that we have these fast following, that is later eluting, significant variants that occur in this biotherapeutic protein. Because we've done this experiment with high resolution, in this case with a superficially porous chromatographic material, we're able to resolve these and look at the high-resolution mass spectral data, in this case online, with an Orbitrap mass spectrometer, in order to deconvolute the data and estimate, measure the exact masses associated with those variants, as well as with the intact and variably glycosylated therapeutic molecule. So this really underlies why we need better mobile phase conditions and chromatographic materials so that we can chromatographically resolve those variant materials and feel greater confidence in our deconvoluted mass spectral data. Just want to quickly indicate that even though we've really focused on the use of this for peptide analyses and intact IgGs, that of course exactly the same alternatives or features in terms of mobile phase modifications can be applied at different levels of protein structure determination. In this case, looking at a light and heavy chain separation, you can find the details in the reference at the bottom of this slide for an IgG monoclonal antibody heavy and light chain separation and the associated mass spectral data, in this case using ammonium formate formic acid mixture as the mobile phase modifier. Same thing can be done using difluoroacetic acid with similar chromatographic performance, desirable characteristics. And also shown on the bottom here is the reason why we've looked a little further afield in terms of acid modifiers is that the formic acid-based separation is rather poor, the peaks are broad, and in fact recovery is inadequate. Same thing can be done in terms of high resolution mass spectroscopic data and high performance separations for the more recently popularized use of IDE protease in order to characterize glycosylation and primary structure variants in monoclonal antibodies. This is becoming a fairly standard methodology. So with that, because we're running short on time, I'll skip to the end and summarize. Improving protein LC-MS is, I hope I've convinced you, both the materials and the chemistry undertaking. We actually like the use of difluoroacetic acid as our current best practice in the lab, and we've used it for more than 2 years in the lab now with no detrimental effects. Beneficial effects in fact, relative to trifluoroacetic acid, in terms of the sensitivity for mass spectrometry and ease of eliminating the material from the hardware. The use of superficially porous materials, particularly those with large pore size, we have found to be greatly enabling in terms of allowing faster separations with higher efficiency. And with that, I'd like to thank some of the contributors we have had to this work, both internally at Advanced Materials Technologies, some of our academic collaborators, and as well the support of the NIH SBIR program for the development of some of these chromatographic materials and methods of use. So with that, let me hand it back over to Laura, and I'd like to thank you for your attention.
Thank you very much, Barry, for that informative presentation. In a moment, we'll start the Q&A session with the audience. We'll just have a few minutes for that. But before we do that, I just want to ask everyone in the audience 3 very brief polling questions. And all of you, you can click directly on your screen to submit your answers. So here's the first one. Would you be willing to try an alternative to formic acid as a mobile phase modifier for protein and peptide LC-MS applications? Yes or no? Once again, would you be willing to try an alternative to formic acid as a mobile phase modifier for protein and peptide LC-MS applications? Yes or no? And you can click directly on your screen to answer. Okay, let's move to our next one just because we're short on time. Here's our next one. Which column manufacturer do you prefer for your protein analysis? Waters, Thermo Fisher Scientific, Phenomics, Agilent, Advanced Materials Technology, Toso Bioscience, or other? So once again, click on your screen to answer. Which column manufacturer do you prefer for your protein analysis? Waters, Thermo Fisher, Phenomics, Agilent, AMD, Toso Bioscience, or other? Okay, and let's move to our last question. Which column manufacturer do you prefer for your peptide analysis? Waters, Thermo Fisher, Phenomics, Agilent, Advanced Materials Technology, Toso, or other? So before we asked about proteins, now we're asking about peptides. Which column manufacturer do you prefer for your peptide analysis? And click directly on the screen to answer. All right. Well, we just have a couple minutes here. Maybe we can just go 1 or 2 minutes past the hour, but let's start the Q&A now. So here's the first question, Barry. Would there be advantages to using a mixture of DFA and FA?
Yes, Laura, thank you. We have shown an example of that with the hemoglobin separation, but we've also looked at it in greater detail with some of the monoclonal antibody work. And specifically there, we've been focused on sensitivity. We are able to dissociate some of the DFA using formic acid, and hopefully within the near future we'll be able to supply some quantitative statements around that. But generically at this point I can say yes, it's a useful thing to give a go, if for no other reason than to manipulate the selectivity of your separation.
Excellent. In comparing the results of MAB separations using different acid modifiers, why is there such a difference in retention time?
Okay. TFA is a significant, a more significant ion pair reagent than DFA is. Because of that, the stronger association of trifluoroacetic acid as well as its greater I hate to use the term hydrophobicity because it's really surface polarizability in all probability. It just results in greater retention, not just for well, pretty much across the board, whether you're looking at small molecules, peptides, or proteins. The difference there is not based on pKa. They're both strong acids. It is largely based on the hydrophobic interactions that occur stronger with TFA as well as its greater ionization, its greater ion pairing characteristics.
How would you compare the extra MS source cleaning required with DFA as compared to both FA and TFA?
So one of the things I didn't have a chance to go into is TFA is really painful to get rid of out of an LCMS. DFA, we do not see that problem. We can switch, for example, from DFA directly to formic acid mobile phases with essentially no switchover cost in terms of time. When we use trifluoroacetic acid, we have to really clean the system up, and it takes a day to do so. With ammonium formic acid mixtures, you have a little bit more salt in there. We find that, after a while you have to spray down the interface with a water bottle or, a water followed by methanol. So there's a little bit more cleanup and maintenance required, but it's really not that much. Formic acid ammonium formate has been used as mobile phase by small molecule guys for a long time and quite usefully.
The 1,000 angstrom pore size is on a 2.7 micrometer particle. Is there any concern about the fragility of the particle?
Nope. Let me briefly discuss that. So the 1,000 angstrom material is not commercially available as yet. It will be this fall. It is a new product that we are bringing to market, and I feel is a very enabling product. It will have very comparable. It does have very comparable physical stability to all of the superficially porous particles that we have made historically. It will be tolerant to, it is tolerant to operation under so-called UHPLC conditions. So no, it's a tough particle.
Excellent. Let's just do one or two more questions. Do you think that using DMSO in the mobile phase is a good choice to enhance solubility of hydrophobic peptides in MS analysis?
I have kind of mixed feelings about that. There have been examples in literature, and certainly in the proteomics literature in recent years, for the addition of DMSO. It's largely been for reasons other than solubility. But that certainly could help. The DMSO at low concentrations has been observed to be reasonably tolerated in electrospray. But we're talking about a couple of percent, I think. If you now start dealing with higher concentrations that might really affect aggregation or solubility of highly hydrophobic materials, I think you're going to run into some problems with getting controlled droplet formation and effective ionization. The other thing that I would be cautious about with DMSO is that there are a number of impurities that will accumulate if DMSO is not used fresh and is not maintained in a non-oxygenated environment. I have not used that myself for MS as much as I have for regular chromatography, or so not electrospray ionization, where I found DMSO to have some reasonable characteristics.
Excellent. Well, Barry, I think we should wrap up. Thank you so much for answering those questions and for your excellent presentation today.
Okay, thank you for attending and giving me your attention. And if you would like to get in touch with any of us, please feel free to do so.
Great. And Barry's email is right on the screen right now. And I'd also like to thank our sponsor, MacMod, for making today's educational webcast possible. Today's webcast will be available for on-demand viewing through July of next year. You'll receive an email from LCGC alerting you when the webcast is available for replay. We invite you to forward that announcement to your colleagues who might have missed today's live event. We hope to see you all next time. Goodbye.